Hello, and welcome to my chemistry screencast on galvanic cells, also known as batteries. And this will be covered in the topic of electrochem. So first of all, we're going to start off with what is electrochem. Electrochem is using redox reactions to generate electrical current. Just a reminder, electrical current is the flow of electrons. So galvanic cells, or as you know them better as batteries, are also known as voltaic cells or electrochemical cells, because we're using a chemical reaction to produce electricity. And how do they work? Well, they work because you can separate the oxidation reaction and the reduction reaction and have the electron transfer occur through a wire that connects them. That allows somebody to, by controlling the route the electrons take, you can then use that flow of electrons to power things. So this is a standard drawing of a galvanic cell. And some of the things that you'll notice these two compartments here. So there's a compartment down here, and there's a compartment down here. And when I draw a galvanic cell, I usually draw my anode on the left and my cathode on the right. So this compartment down here is called on the left is called the anode, and the one on the right is called the cathode. And you can actually have the cathode on the right and the anode on the left, but to make things more consistent when I do them, I like to keep the anode on the left and the cathode on the right. You'll notice these square things in here, and those are called electrodes. So we have one electrode here, and we have another electrode all the way over here. And we have this tube that connects the anode and the cathode, and that tube is called the salt bridge. And then you also have this black line connecting the electrodes, and that black line is a wire. And that controls the path that the electrons take. This white box here is a voltmeter, or other use for the voltage. Sometimes you'll see a light bulb here. So you could have a calculator there. You could really have anything there. A lot of times, though, in pictures, it'll be a voltmeter. So the two compartments, and the compartments, we're going to talk about what each of these things does, contain both the electrode and the solution. So we'll start talking about the anode first. The first one was the anode. And the anode is the site of oxidation, or the oxidation half reaction. And because it's the site of oxidation and it loses electrons, it will have a negative charge. And the other compartment is the cathode. And that is the site of the reduction half reaction. And because the reduction is the gain of electrons, has a positive charge. And so we'll write the negative charge down here, and we'll write a positive charge down here to remind us that the anode is negative and the cathode is positive. And so we also have the wire, and the wire, just electrons are transferred. It has place of it transfers the electrons from the anode to the cathode. And the electrons will always flow from the anode to the cathode, so I like to think that they flow in alphabetical order. They go from A to C. So in our picture, we would draw that in as well. You can usually just draw that in as arrows along the wire, but then you'd also put a little, label them with a little E minus, so the person that's looking at your picture knows that you're talking about electron flow. And the last thing that we need to talk about is the salt bridge and what it does. So the salt bridge contains a salt, which, as you know, is an ionic compound. And so it contains ions. So it has allows for ions to move into the compartments. And by doing that, it prevents the buildup of charge. And additionally, it also completes the circuit. So if you don't have the salt bridge, your galvanic cell is absolutely not going to work. So it contains positive and negative ions. So the anode, it has a negative charge, but it's losing electrons. So as it's losing electrons, it's going to become more positive, which means that the negative ions are going to move from the salt bridge into that anode to replace that charge. And in contrast, on the cathode side, the positive ions in the salt bridge, because these are gaining, the side's gaining electrons, you're going to have the negatives being built up in here, and so you're going to have those positive ions flowing in to the cathode to neutralize that charge. Now let's talk about cell potential. Cell potential is the amount of voltage or the amount of energy or electricity that can be generated by a cell. So the amount of electricity that can be generated by a cell. And so we represent this in equations with a fancy E or epsilon, and most of the time you're using this naught sign, which, just like in thermo, it means standard state conditions. So that's 298 Kelvin, 1 molar solutions. And how is this cell potential generated, or this electricity generated? Well, the oxidizing agent is the substance that gets reduced. Poles that oxidizing agent actually pulls electrons through the wire from the reducing agent. And that reducing agent is the substance that gets oxidized. And so we measure this electrical amount in volts, and volts are represented with a V. And something that's going to help us later on is 1 volt is equal to 1 joule per coulomb. And coulomb is a unit of charge. You should be familiar with joules as a unit of energy. So it's the amount of energy per a specific amount of charge. Now, how do we go about calculating this cell potential? It's also called the standard reduction potential. So you use standard reduction potentials to calculate the cell potential. So the standard reduction potentials are always written in reduction form. Which means that you're going to have the electrons on the reactant side. So it's always from the standpoint of gaining electrons. And there's a list of standard reduction potentials in your textbook in the appendices. And that's just what the standard reduction potential is it's the voltage produced from a reduction reaction or reduction half reaction. And there's a table in the textbook that has these. And like I said before, it's abbreviated E naught. And again, that naught means standard state conditions. Okay, so when finding the cell potential, the coefficients must equal those found in the balanced equation. And that's going to be important because we're going to be doing a calculation that's very similar to Hess's law, but a little bit different. So we'll go ahead and work on one. How do you calculate the standard reduction potential for this reaction? So the first thing you're going to do is you're going to divide the reaction into half reactions. So Fe3 plus is more similar to Fe2 plus. And since the atoms are already balanced, we just have to add a balance of charge. A positive 3 charge here, positive 2 charge here. We need to make this one smaller. So we're going to add an electron to the left side. The other half reaction is copper solid goes to Cu2 plus. Again, our atoms are balanced right away. And then we're going to add 2 electrons here to neutralize that positive charge. So when we're dividing this into our half reactions, we're essentially balancing the equation. So we need to make sure that our electrons match. So I need to multiply this by 2. So I will have, when I balance my equation, I will have Cu plus 2 Fe3 plus goes to 2 Fe2 plus Cu2 plus. So now I have my overall balanced equation. Then I'm going to look up each half reaction in my appendices and find out the E naught value. So when I look those up, I find that the E naught for this reaction, and when you look up this reaction, you're going to find it written as E minus plus Fe3 plus yields Fe2 plus, and you're going to find that that is an E naught value of 0.77 volts. Now, this reaction, when you go to look it up, you'll never find it written like this because the table of values is written with the electrons on the left. So you're going to have to look up Cu2 plus 2 electrons yields Cu. And when you look that up, you're going to find that that you get a value of positive 0.34 volts. But because when we balance this equation, we have to flip the reaction, you also have to reverse that sign. So E naught is going to equal negative 0.34 volts. And then to find the voltage, you're going to add these two up, just like you would add up your just add those up, just like you would add up your delta H values if this was a Hess's law problem. Now, one thing to note, and when you do that, you end up getting 0.43 volts. So we end up getting 0.43 volts. Now, one thing to note is that unlike Hess's law, when you multiply by a coefficient, it does not affect the voltage. So if you flip a reaction, you do reverse the sign, but you do not multiply. If you need to multiply a reaction by the coefficient, you do not multiply the voltage by that coefficient. So my E naught for this reaction is my 0.43 volts. Okay. Now, another thing that you'll be asked to do is to describe a galvanic cell, which means you have to actually draw the galvanic cell from the equation. So you'll be given an equation, a redox reaction, and you have to use that to describe or draw and label the galvanic cell. So things that you need to include in your drawing. You need to include the cell potential and the balanced reaction. Most of the time you're going to be given an unbalanced reaction. So the cell potential, remember that this right here, that's our voltage. So you need to calculate the voltage and give a balanced equation. And that's exactly what we just did in the previous example. So see previous example. That's nothing new. Okay. Then you're going to have to label the direction of the electron flow. And remember that electrons always flow from anode to cathode. So that means you're going to have to identify the anode and identify the cathode. You're going to have to designate the anode and the cathode. And that's going to help you with your direction of electron flow. And you need to label the electrodes and the ions present in each compartment. So what that means is for the electrode, you're going to have to label the metal. And you can't just label it as metal. You have to label the actual metal that it's in and that makes it up. One thing to note with the electrodes, they are made of the metal that's found in the half reaction. And if there's no metal in the half reaction, you're going to use platinum. The reason you use platinum is because it's a very non-reactive metal, so it's going to transfer the electrons, but it's not going to change any of what's reacting. And how you're going to do that is things that you need to know is that for a galvanic cell to run spontaneously, the voltage needs to be positive. And that makes sense that we would want a positive voltage for a battery. So when you're given the half reactions, you need to flip the one that's needed to make a positive E0 of the cell, which means you're going to flip the half reaction that has a more negative cell potential, or E0. This half reaction that gets flipped will be the oxidation half reaction. So that means that the compartment that holds that half reaction is your anode, because oxidation happens at the anode. And the way that I remember oxidation happens at the anode is that that oxidation and anode both start with vowels, and reduction and cathode both start with consonants. So the vowels go together and the consonants go together. All right, so now we're going to go through this process and actually draw one out. So if we have these two half reactions and you're given the voltages here, it says describe the cell from the following half reactions. So the first thing that we're going to have to do is balance this reaction. And because we want this to be a positive voltage, we're going to flip the one that's more negative. So we have a negative 0.44 in this top reaction and a positive 1.51 volts in our bottom reaction, which means that this one is more negative. So we flip this one. So we're going to rewrite that flipped. So Fe is going to go to Fe2 plus 2 electrons. And when we do that, our voltage changes to positive 0.44 volts. And then we're going to balance the overall reaction now. Because you're given the half reactions, you know that they are at least the half reaction is balanced for both atoms and electrons because they already have the electrons in them. But now we need to have the electrons that are transferred be the same amount. So we have 5 electrons in the reaction that has permanganate in it, and we have 2 electrons in the reaction that has iron in it. And so to make them the same, we're going to multiply this by the permanganate ion reaction by 2, and we're going to multiply the iron reaction by 5 to get our least common multiple there of 10. And when we do that, we will get 2MnO4 minus plus 16H plus, the electrons are going to cancel, plus 5Fe yields 2Mn2 plus 8H2O plus 5Fe2 plus. And then we can add these reactions together, or our voltages together. So our E0 is going to be 1.51 plus 0.44 volts, or 1.95 volts. So we now have our voltage for our cell. Now we have to draw the cell. And because I don't like having to draw a salt bridge every time because that's kind of a difficult drawing, I'm going to show you a shortcut that you can use. So we're going to draw a big rectangle to make up the two compartments. And then we're going to draw a stripe down here. And this stripe, instead of having a salt bridge go through, we're going to label this porous disc. And so because it's a porous disc, it actually allows for that ion transfer as well. Okay? And then we need to draw in our electrodes. And a wire that connects the two electrodes. Now, like I said before, I like to have the anode on my left. I like to just label that as the anode and label the right side as the cathode. So my anode will be negative, my cathode will be positive. And then we need to put the substances that we have in here. So my anode is the site of oxidation. So that's going to be the reaction that I flipped. So this one is my oxidation reaction, and the one that has a permanganate is the reduction reaction. So I'm just going to start filling this stuff in. My electrode is my solid metal on my oxidation side, so that's going to be iron. So I'm going to label that as Fe. And then inside my solution, I'm going to have ions. So the only thing that I have listed as an ion in this whole reaction is the Fe2+. So I'm going to put that in my solution section. Because I'm making anode, remember electrons flow alphabetically from anode to cathode, putting it in my electron flow. And so then the other electrode, if I go look here, I don't have any solids. Permanganate's an ion, electrons are electrons, H plus is an ion, Mn2 plus is an ion, and water's a liquid. So right now I don't have anything from my half reaction that can make up my electrode, which means that I'm going to use my platinum in that situation. And then all of these ions that are listed here need to go into my cathode container. So I'm going to have MnO4 minus, I'm going to have H plus, and I'm going to have Mn2 plus. And then the last thing that I have to show is the movement of ions in my salt bridge. So I'll have a positive ion and I'll have a negative ion. And the positive ions will go to the cathode and the negative ions go to the anode. So you just draw them moving. And then you have your completed galvanic cell with your balanced equation, your voltage, and everything that you need labeled. So this leads to cell potential, electrical work, and free energy. And so we're going to bring back some concepts from thermo. Energy is the capacity to do work, just reminding you. And in a galvanic cell, that's caused by the flow of electrons. And we measure that by the potential difference between the anode and the cathode, and that's really just a fancy way of saying voltage. So this is really just your voltage. Okay, so this energy that we're talking about is the voltage. And remember from earlier that 1 volt is equal to 1 joule over 1 coulomb. And just like in thermo, when we had positives and negatives that meant something, it means something in electrochem as well. So we are using thermodynamic notation. So if a system does work, what happens to the energy of the system? Well, just like if you or I have to do work, our energy goes down, our energy decreases. So that means that the energy of the system will also decrease if it has to do work. And as a battery runs, it is doing work. So that means that the sign for W is going to be negative. Because if you're decreasing the energy, then the sign for W is going to be negative. But the sign for epsilon, or our voltage, is positive. And the maximum work from a cell is obtained from a maximum cell potential. So if a cell produces voltage, is the system spontaneous? Well, yes, we know that that is spontaneous because that's what we were looking for, a positive voltage in order to get the system to spontaneously produce energy. And if it's spontaneous, what does that mean about the sign of delta G? Well, if we remember back to thermochem, that means that delta G is negative. So how can this help us with the relationship between, figuring out the relationship between our voltage and our delta G value? It means that they are opposite signs. Okay, and it actually brings us to an equation that delta G is equal to negative N F E. And N is the moles of electrons being transferred between the anode and the cathode. F is something called Faraday's constant. And Faraday's constant is that 1 mole, but there's 96,485 coulombs of charge for every 1 mole of electrons. And then E naught is the voltage of the cell. So, in an example, how do you calculate the delta G for this reaction? So the first thing we need to look at is we're going to look at what delta G is equal to. It equals negative NFE, which means we need to find the voltage before we can do that. We also need to find the moles of electrons, and we're going to find the moles of electrons in the process of balancing this equation and finding the E. So we're going to have Cu2 plus going to Cu solid. We know that we need to add 2 electrons over on the left side here. And then we're going to have Fe solid going to Fe2 plus. And we're going to have to add 2 electrons over on the right side. And then we're going to look these values up. When we look these values up, we find that E naught for the copper half reaction is 0.34 volts. And the E naught for the iron half reaction is 0.78 volts. when you add them all up, you have we get our reaction here, which is already balanced. But to find our overall voltage, E naught is going to equal, oh, hold on, I messed up. Okay, so we're going to do this reaction here. And before we can do this, we need to know that delta G is equal to negative NFE, which means we need to find the voltage and we need to find the moles of electrons that are transferred. We're going to find the moles of electrons that are transferred by making sure that this equation is balanced and in the process also finding our voltage that's produced. So our first half reaction is between copper ion going to copper solid, and to balance this, the atoms are balanced but the charge is not, so we have to add 2 electrons to the left side. And then we have our iron half reaction, and that goes from iron solid to Fe2+. We're also going to add 2 electrons to the right side. And when you look up the voltage of these, you're going to find that the copper half reaction, it's already in reduction form, so you would find it exactly as it's written, has a voltage of 0.34 volts. And if you look this one up, you'd be looking at Fe2+ plus 2 electrons yields Fe, but we need to flip that, so we change the sign of what we have of a negative 0.44 to positive 0.44 volts. And then we add these together and we end up getting 0.78 volts. Now we can plug this in here, and we can also look at our half reactions and find out what our N value is. So that means delta G is equal to negative. In here we have 2 electrons being transferred total, so it's going to be negative 2 times F, we said is a constant of 96,485, and that's this is moles of electrons. This is coulombs per mole of electrons. And then our voltage is 0.78. 1 volt is 1 joule per coulomb. So that's joule over coulombs. So our coulombs cancel out, our moles of electrons cancel out, and we get delta G is equal to negative 150,000 joules. And that's all for today's screencast on galvanic cells. If you have questions, please bring them with you to class, and I will gladly answer them.